Hello everyone, my name is B. Jaydir. Today my topic is buffer allocation in merge sorting. Buffer allocation in merge sorting. A fixed buffer allocation for merge sorting is presented here, which minimizes the number of input-output operations for a given order of merge. When sorting on the movable arms disks, the number of seeks is equal to the number of input-output operations, and the seek time usually controls the sort time. First, some standard terminology is introduced, then the input buffer allocation method is described, followed by an analysis of the important to be expected over more conventional allocation. This analysis makes use of a particular distribution function. An analysis of a complete different distribution is given, which yields similar results. This suggests that the results do not depend on a particular distribution function. An optimum output buffer size is also determined. It is concluded that this buffering allocation can significantly reduce the time of merge sorting on movable ARM disks when the input data are not random, and that this is output buffer allocation should be used whether the data is random or not. A file is comprised of items. Each item contains one or more keys. The file is ordered according to some rule involving the keys ascending or descending order. A string is a set of ordered items, that is a sorted subtype. A merge sort a program is comprised of a pre-sort which produces strings, and a merge which merges these strings in one or more passes until on merge sort program is comprised of a pre-sort which produces strings, and a merge which merges these strings in one or more passes until one string or sorted file is produced. Other techniques can be used such as radix sorting, which virtually all sort programs in production today use it for the sorting large files. A file which cannot be sorted in internal memory of the computer uses a merging technique, while the pre-sort is usually compute bound. In contemporary equipment, the merge passes are usually input-output bound. Most present-day pre-sort programs will produce strings of a varying length. In fact, they will produce only one string if the original file was in sort or nearly so. Allocation of input buffers at the beginning of a merge pass. It is determined that what order of merge, how many strings will be merged at one time will be used. Suppose strings are to be merged at n at a time, and s is equals to I 1 comma 2 comma and so on to n is the length of the string. The same technique is repeated if there are more than n strings. Let f is equals to I. F will be the entire tile if this is the last merge pass. Then no matter how the buffers for the various strings are allocated, the total amount of data to be transferred is constant, so that the data transfer time is constant. However, each individual read involves an access time. This can be latency time on head per track drum or disk, seek time on the other drums and disk, start stop time on tape, etc. By far the most important of these is the seek time on a single head disks. If an area T is available for input buffers and B I is equals to 1, 2 and so on is the buffer area allocated to the ith string. Then from the definition we have T is equals to 1. The number of reads required for the ith string is S by B, or twice that if the double buffering is used. Therefore, the total number of reads is R is equals to E is equals to IR, E is equals to IB. Conventionally, the buffer are allocated equally so that the B is equals to T IN, which gives N F R EI S is equals to T if the first n minus 1 buffer areas are considered independent variables, and if B is equals to T is equals to Z. Comparison in order to measure the improvement to be expected using this allocation. It is necessary to express the read time as a function of the variance. If the analysis that follows, it will be assumed that the string lengths obey a gamma distribution. A strong argument justifying this assumption cannot be given. It does satisfy the condition that the string length cannot be negative and that a string can exceed any given length, provided the presort permits this. Furthermore, it rises rapidly from the zero to a maximum and then asymptotically approaches the abscissa as would be expected. Finally, it is the simplest distribution function which satisfies these constraints. At any rate, it has more to justify it than the assumption that the data are random and the strings are nearly all the same length. Using conventional buffer allocations, the number of reads was nf by t. Let the ratio of improvement be a, so that x is equals to 1, r is equals to nf by t. Naturally, the larger the variance, the greater the improvement. However, an intuitive argument can be made to substantiate this result for small values of the variance without recourse to the gamma distribution. It is desired to obtain r as a function of a, then this result, if such a function exists, should not depend on a particular sample from the output buffer. Since the output is usually written sequentially, the read time is generally much greater than the write time. This is not sufficient. This is not the case. However, if the output is written on the same physical unit as the input, an undesirable situation, it has tactically assumed that all the input output time other than the actual data transfer time was due to seek time. This has no mattered up to the point. However, in the normal case where the output is a separate physical unit, writing the output does not involve any seeks. Every input-output operations does not involve a latency time to that, and determining the output buffer size depends on the ratio of the latency time to the seek time. Let O represents the seek time and U represent the latency time. If C is the total area available for the buffers and B is the output buffer size, then C is equals to B minus T minus T. Then the number of writes, W is clearly f by b, and from the previous sections, a is equals to f by t. Then the total input output delay time, input output time exclusive of the data transfer is. If the variance equals the mean, the number of accesses is reduced by 25%, while if the variance equals twice the mean, the number of accesses is reduced by 50%. If the variance is 0, this technique is equivalent to the standard technique as would be expected. It is interesting to note that this is non-randomness actually serves to reduce the sort timing as long as it does not cause more strings to be produced. Both the computation time and the storage required to implement this technique are negligible. Since the number of accesses is never increased, this buffer allocation technique can be used to advantage in any sort where the larger variance in string length can be anticipated. The method of allocating the output buffer is valid even if the file is random. This is numbers indicate the order in which the steps are proceeded. Thank you.